All right. So a rational function is a function of the form r of x equals p of x over q of x. So they are polynomials, but in the form of fractions. P and Q are polynomial functions, and the domain of R is all real numbers except any real number which would make the denominator 0, right? So we're going to practice by stating the domain of these 3 examples, okay? We are just studying the characteristics of the graphs of the functions so that in the end, we can graph rational functions ourselves without using technology, right? You use Desmos just to verify your answer at the end.
One of those many steps.
Make sure you're on mute. And again, domain just means the possible replacements for X or inputs, and exclude any value that causes the denominator to equal 0. State the domain. What can X be, excluding anything that makes the denominator 0? Okay, exclude and I know we all know this. Exclude values that will make the denominator 0. That would be undefined. All right, here is example A, example B, and example C, since they're all R of X. Okay. For A, we have R of X equals 3x squared minus 5 over x plus 2. So we are just looking at the denominator. The denominator right now is x plus 2. What value of x would make the denominator 0? Well, you can take the denominator and set it equal to 0. X plus 2 is 0. That means that when x is a -2, because we subtract 2 from both sides to get x alone, when x is -2, our denominator would be a 0. So we are going to say that the domain is x such that x cannot be the one number that would make it 0. When they ask you to state the domain, you're saying it's all real numbers except x such that x cannot be -2. Good. Example B, we're looking at 1 over x squared minus 25, but they have this, they've put in standard form first. And then this would be factored form, right? Because we know that the difference of 2 squares is, if this is a squared and this is b squared, and it's the difference of them, then we can say it's the same as a minus b times a plus b, right? So they just took the standard form of the difference of 2 squares and put it in factored form. Factored form helps because it makes our work simpler, right? For each factor, what do I need to exclude? So x minus 5 times x plus 5 cannot equal 0. That means neither x minus 5 nor x plus 5 can equal 0, right? We have 2 situations. We have x minus 5 cannot be 0, so x cannot be positive 5, and x plus 5 cannot be 0, so x cannot be -5. You see how putting it in factored form makes it a bit simpler to find what we need to exclude? So here for B, the domain is x is all real numbers except -5 and 5. So we're excluding -5 and 5 from the domain because either of those right here would make it 1 divided by 0, which is undefined. Letter C, we have 2x to the third over x squared plus 1, right? What value can you square and add 1 to it to make it 0? you can square it and add 1 to it and make it equal 0. -1. It might come to you, right? Like this one came to you, it's just -2. This one's +5 and -5. This one, if it's not just coming to you, you can remember, you can just set it equal to 0. So x squared plus 1 equals 0. So we'll move the we'll move the +1. So we'll subtract 1 from both sides. We get x squared equals -1. To eliminate the squared, we're going to take the square root of both sides. Remember, when you take the square root of both sides, you need to add and subtract the answer, because there are 2 possible answers to get 25, right? It could be a -5 squared becomes 25, or a +5 squared becomes 25. So that eliminates that, and we just have x is plus or minus the square root of -1. However, remember, we are not using imaginary numbers on the coordinate plane, so there is no solution to the square root of -1, because it's a non-real answer. Good. So on the coordinate plane of xy, there is no number that you can square, add 1 to, and get 0. Right? Because if you have squared it, you now have a positive number, or you have 0. 0 plus 1 is 1. If you took -1 and squared it, you would get a +1. 1 plus 1 is 2. Okay, so here the domain is all real numbers. X, such that x is any, I think this is how my math lab says it, any real number. Okay, so the domain is, for here, it was that x cannot be -2. Here it's x cannot be -5 and x cannot be 5. And here it's x is all real numbers. Good. All right. I said we would be talking about asymptotes today. An asymptote is when a graph approaches but never touches an x value in this case. Okay. The graph of a rational function in lowest terms, when they say in lowest terms, they mean it has been factored and simplified. It has a vertical asymptote at any value that makes the denominator 0. Okay. The graph will not touch or ever cross a true vertical asymptote. Okay. Now, multiplicity of vertical asymptotes. We talked about multiplicity in 5.2. The multiplicity is just the exponent that factor is raised to. Okay. If the multiplicity of the factor that yields the vertical asymptote is odd, then it approaches infinity on either side of the vertical asymptote. Opposite sides on either side of the vertical asymptote. If it's even, then the graph of the function will approach infinity on the same direction and opposite sides of the vertical asymptote. Okay, so this one, odd, it's going in opposite directions. These pictures are a bit out of order for how I read. If it's even multiplicity, they are going in the same direction as they both approach the same number, the same x value. Good. So if we were to describe this, this would be that both sides of the graph are headed towards positive infinity, going the same direction on the y-axis, right? So this is even multiplicity. Here, however, on the left, we are approaching negative infinity, right? On our y values. And on the right, we are approaching positive infinity. As we get closer and closer to the asymptote on the y-axis. So this is an odd multiplicity. If your exponent is odd, it's going to look like this. If it's even, they're going to go in the same direction. Okay, so an example of an even multiplicity might be x over x minus 1 squared, right? The even multiplicity is that 2. The odd multiplicity you might see more frequently because it's just x over x minus 3 raised to the first power, or x over x plus 1 to the third power. So you might see it more often because it's just not raised to any power. Even multiplicity, odd multiplicity, what the graph will do. In lowest terms, remember, factored and simplified. So you have removed any factors that were common to the top and to the bottom of the fraction. So for example 2, they're just asking us to find all vertical asymptotes and then look at the graphs to make sure that we are correct. Good. The first thing you want to do, remember that it said the vertical asymptotes we check after they have been factored and simplified. So if possible, factor first. Step 1 is factor the polynomial on the top and factor the polynomial on the bottom, and then simplify it by excluding common factors. Yes, of course, that is okay. Thank you for letting me know. Factor, you could say and simplify if you want. Eliminate common factors. Good. All right, let's look at letter A. Letter A is f of x equals x plus 5 divided by x minus 3. We have factored it. After you factor it, you want to find the domain. And anything that's included from the domain, I apologize. Anything that is excluded from the domain will be your vertical asymptote. Okay, so letter A, f of x equals x plus 5 divided by x minus 3. We don't have anything to, it's in factored form and standard form. There's nothing to cancel between the top and the bottom, right? No common factors. So the vertical asymptote will be where the domain the vertical asymptote will be the term that we have eliminated from the domain. Okay, so any value that we find x equaling when we have set the denominator equal to 0 will be our vertical asymptote. Good. Just so we practiced it. Right here, right? So if this is x cannot be -2, then we have a vertical asymptote at x equals -2. That's what we're doing here, okay? B, we said x can't be -5 and 5, so that means we have a vertical asymptote at x equals -5 and x equals +5. Good. C, no vertical asymptotes. So that's why we practice finding the domain, because anything you're excluding from the domain is going to be an asymptote in this case after you have simplified it. So just like we did in those first 3 examples, A, B, and C, we're just going to find the domain. For letter A, my domain is, again, x minus 3 is 0, so x cannot be a +3. So x such that x cannot be a positive 3. We found the domain. So we have a vertical asymptote at x equals 3. Now remember we're looking at the multiplicity. What is the multiplicity of x minus 3? It's a multiplicity of 1. That's an odd multiplicity, which means that they are approaching from opposite directions. So at x equals positive 3, we're going to see something like this. Or that. Those are our two options. Good. That's what it means by opposite. One's going up, the other's going down. Let's now look at B. B is Rx equal, R of x equals x over x squared minus 49. Again, just like we saw, x squared minus 25 is the difference of two squares. So we can say it's x minus 5 times x plus 5. This is also the difference of two squares. So I'm going to call this x over, the squares are x, and the square root of 49 is 7. So x plus 7 times x minus 7 is the factored form of x squared minus 49. Okay. So B is that my domain is x such that x cannot be, and you can just kind of see it, right? X cannot be negative 7 and x cannot be positive 7 because we took the difference of two squares, we factored it, and we got x plus 7 as one of the factors and x minus 7 as one of the factors. So we are excluding a negative 7 and a positive 7 from our domain. That means we have two vertical asymptotes, a vertical asymptote at x equals negative 7, vertical asymptote at x equals positive 7. Look at each of them individually. X equals negative 7 is this one. What is the multiplicity of that one? They happen to be the same. Your multiplicity is 1, which is odd, which means it is opposite, approaching from opposite ends. Again, multiplicity of 1. This guy, out of frame. This guy has a multiplicity of 1. It's odd, so it's again approaching from opposite ends. So what it's going to look like is maybe here is here's God, ugly. Here is negative x equals negative 7. Here is x equals 7, right? And it might be doing this. And then of that. And of that. For example, for B. Okay. So they're going in opposite directions. So it's up and down, up and down. Letter C is h of x equals x squared divided by x squared plus 9. All right. So that is not the difference of two squares because those are being added, right? So you can just like we did here. Here we did x squared plus 1. Here you can do x squared plus 9. And what happens? When we did x squared plus 1, what happened? Set it equal to 0. Subtract that 9. X squared equals negative 9. Now what we need to do is take the square root, including a plus and a minus. But when we take the square root of a negative number, it does not any longer exist on the coordinate plane. So we just say that our domain is all real numbers. So there will be no vertical asymptotes on this. If I put that into a graphing utility, I would not see any vertical asymptotes. Good. Okay, so letter D looks like for all of these, we've only been able to factor this one, and we did it pretty quickly because it was the difference of two squares. Here we have x squared minus 25 over x squared plus 2x minus 35. Okay, let's see if we can factor and simplify g of x. So factor the top and factor the bottom and see what we get. Okay. G of x, can we see it? Equals x squared minus 25 over x squared plus 2x minus 35. So there's only one way to factor this. It's the difference of two squares, right? So it's x plus 5 times x minus 5. If I think about that and I think that I'm trying to factor out any common factors, that means that this is 35, A is 1, B is 2, C is negative 35. So I'm probably either going to have a positive 5 or a negative 5 as one of my factors of negative 35 in order to cancel one of these. But you can just do it the old-fashioned way. So we want it to multiply to equal negative 35, and we want it to add the two terms to add to equal 2, right? So we can say it's, well, we kind of know, right? It's not going to be negative 1 and positive 35. It's not going to be, you can't divide it by 2. You can't divide it by 3. You can't divide it by 4. So it's going to be negative 5 and positive 7, right? Because when you combine a negative 5 and a positive 7, you get a positive 2. So that factors to x minus 5 times x plus 7. Good. Okay, now it says simplify. So that means that this x minus 5 and this x minus 5 cancel out. And what we are left with is x plus 5 over x plus 7, which looks a lot like A, where it was very quick to find it, right? The domain is x such that x cannot be, right? X cannot be negative 7. Done. There is going to be one vertical asymptote at x equals negative 7. It has a multiplicity of 1. So it's an odd multiplicity. So they're going to be going in opposite directions. I'm going to pause the recording because I'm putting these all into decimals. So if you're watching the video, put these all into decimals. Okay, so let's look at A. We said that there is going to be a vertical asymptote at x equals negative, or sorry, I'm looking at B. We said there's going to be a vertical asymptote at x equals 3, and that is going to be opposite. So if you look at that, you can see that that's probably x equals a positive 3, and that those are opposite. Those asymptotes are going the opposite directions. B, we said that we'll have two vertical asymptotes at negative 7 and at 7, and they'll be going in opposite directions, which is what that looks like. Here, we said there are no vertical asymptotes. And then for our last one, we said that there is going to be a vertical asymptote at x equals negative 7. And I just want you to notice what happens at x equals a positive 5, right? Because we eliminated x equals negative 5 from the top, or sorry, x minus 5 as a factor from the top and the bottom. So what if x was at negative 5? Ooh, hold on. We eliminated x minus 5, sorry. We eliminated x minus 5, so is x equals 5 on this graph? It's not, it's actually it doesn't exist on the graph. If you put in 5, it's actually undefined. So it's a hole in the graph, but it's not an asymptote because it was a factor that we factored out, common to the top and the bottom. All right. All right, so that's what it means by verify using a graphing utility. You should be able to see everything you found is true. All right, horizontal or oblique asymptotes. This can sound very complicated. We know how to find vertical asymptotes as well. Excuse me, as well as whether they're approached from the same direction or from different directions. So the same direction is if the multiplicity is even, right? And then opposite directions would be if the multiplicity was odd. And that's for vertical asymptotes, okay? Now we're going to talk about horizontal or oblique asymptotes. Oblique, in this case, just means slanted. So these were vertical. It's a very vertical line. You're approaching it forever. Horizontal, sorry. Something along the x-axis, for example, right? And then oblique means it's a slanted line. Horizontal and oblique asymptotes are asymptotes that can be crossed. The vertical asymptotes are approached and never crossed. Horizontal and oblique asymptotes just show us the end behavior. They show general end behavior, but can be crossed. So when you zoom out on your graph, you'll see that you're approaching your horizontal asymptote or you're approaching your oblique asymptote, even if your graph did cross that asymptote. Do we have horizontal or oblique asymptotes? It depends on, so here, vertical asymptotes obviously depend on the domain of your function. The horizontal and oblique asymptotes depend on the degree of your numerator and the degree of your denominator. Remember that your degree is the largest exponent in that polynomial, okay? Yeah, they just describe the end behavior of the graph. They can touch it, they can cross it. And I'm gonna read this, but let me see where I wrote it down. I also want to write it down in hopefully a simpler form for you. Okay, so think about what we're working with, okay? We have f of x is a times x to the power of n over b times x to the power of m. All right, write this down. This, as we know, is our this is the numerator, right? This is our denominator. So how do we decide whether or not we have a horizontal or oblique asymptote and what our horizontal or oblique asymptote is? It depends on the degree of the numerator and the degree of the denominator. You could even call that D if you wanted to instead of M, because that's a numerator and that's a denominator. Okay, here are the rules. If the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equals 0, which is the x-axis. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote. And it is important to know whether it's a horizontal asymptote or an oblique asymptote. So that's your first case. All right. Second case, if the degree of the numerator is this, so if the degree of this is the same as the degree of this, then there is a horizontal asymptote located at y equals a divided by b. The leading coefficient of the numerator divided by the leading coefficient of the denominator. All right. So if n is the same number as m, then you have a horizontal asymptote at y equals a over b, according to this. Okay, so take this number, put it here, take this number, put it here. Remember, this must be in standard form, standard form. Okay, not bad, right? Okay, that makes sense. Third case, if the degree of the numerator is equal to the degree of the denominator plus 1, then you have to divide all of this number by, or sorry, all of this polynomial by this polynomial, and your y equals mx or ax plus b is the oblique asymptote. Okay, so if n is equal to m plus 1 exactly, then you have a oblique asymptote at y equals mx plus b, just to remember that it's just a straight line, because you divided is an oblique asymptote found using division. Yeah, because you divided all of your numerator by all of your denominator until you got an m and a b. Last one, don't worry. That one was the worst one, obviously. If your numerator is greater than or equal to, if it's anything bigger than that, there's none. You can just say none. So if your denominator is any bigger than m plus 1, there's none. You could even write this as if n is greater than m plus 1, none, if that makes more sense to you. 1 second. All right, so make sure that that is written down. That is what you need to know about horizontal and oblique asymptotes. Let's look at example 3. Find the horizontal or oblique asymptotes if they exist, and then put them into Desmos. I don't think we'll put them into Desmos because that's going to take a lot of time. But what we are doing is we are describing the behavior, the end behavior of the graph, just like we were doing in 5.2. Okay. And remember that what we are looking at is the degree of the numerator and the degree of the denominator. So these are already in standard form, right? So we're checking that. Is this number smaller than this number? Is this number bigger than this number? Or is this number equal to this number? So have your little, have the notes we took ready. Just like I do not. All right, we have for our first example, 1, 2, 3, 4. So for number 1, n is equal to 4. And I call that m, maybe you called it d, but m is equal to 6. Good. N is equal to 4 and m is equal to 6. N is less than 4 is less than 6, 4 is equal to 6, 4 is equal to 6 plus 1, or 4 is greater than 6 plus 1. 4 is less than 6, right? So we have a horizontal asymptote at y equals 0. N is less than m. Good. All right. Second one, n is 3, m is 2. N is 3, m is 2. N is less than 3? No. N is equal to 3? No. N is equal to, sorry, 3 is greater, 3 is less than 2? No. 3 is equal to 2? No. 3 is equal to 2 plus 1? Yes. So that means we have a oblique asymptote at y equals mx plus b when we divide our numerator by our denominator. Good. What I need to do here is x squared plus x plus 1. I'm going to put 2x to the third plus 3x squared plus 2. And I'm going to do this long division. I know it looks crazy, but you don't have to do it very long. You just have to get 2 terms, right? You just need m, x, and b out of here. And the way I got this was I copied the denominator first and then the numerator. And I'm going to take the numerator and divide it by the denominator. All right. So if I look at 2x cubed plus 3x squared plus 2, and I have x squared, what do I need to divide, or sorry, what do I need to multiply x squared by to get 2x cubed? I need to multiply it by 2x, right? Take that term, multiply it by all of this. 2x times x squared is 2x to the third. 2x times x is plus 2x squared, right? And then 2x plus 1 is 2x. Good. And then remember, you're subtracting all of that. So those cancel. Positive 3x squared minus 2x just gives me x squared. 2 and a positive 2x. So we're subtracting a 2x, but there was no x. So we're going to say negative 2x plus 2. So my first term of that y equals mx plus b is 2x, right? Now I have x squared minus 2x plus 2. And I'm dividing it into x squared. Sorry. Dividing it by x squared plus x plus 1. So my next term is going to be x squared, and x squared is just going to be 1. Right? And I can stop. I don't need to keep going. I have mx plus b. So this has a oblique asymptote at, I know it was intimidating, but we did it very quickly. Oblique asymptote at y equals 2x plus 1. Okay. Let's look at that one. That one was the, I'm going to delete that. 9x squared minus x plus 1. So they didn't ask about our horizontal asymptotes, but if you then graph the line 2x plus 1. Oh, sorry, it was not that one. That didn't work at all. It's this guy. So you can see that it shows the end behavior because there's the graph, and then there's the graph of the line we found. It follows that graph. Number 3, my n is 2, my m is 2. When they equal each other, we just have a horizontal asymptote at 9/3. The coefficient of my numerator divided by the coefficient of my denominator, 9 divided by 3 is, oh, sorry, horizontal asymptote at y equals 9/3, which is 3. So if I put that into Desmos and I put y equals 3 into Desmos, you will see that the end behavior follows and is near y equals 3. Good. And our final one, n is 5, m is 3. So looking at our list, 5 is less than 3. Oh, sorry, make it so you can actually see it. 5 is less than 3, 5 is equal to 3, 5 is equal to 3 plus 1. None of that is true. It's that 5 is greater than 3 plus 1, right? So that just means there are none. Okay, let me show you just on Desmos really quickly that this graph does follow y equals 3, and then you are free to go. So it was this one, and then we'll just put in y equals 3. So the further you zoom out, it remains on that line.